So imagine building a global load balancer for a massive enterprise network.
Oh man.
Right. But instead of, writing the routing rules, instead of meticulously defining all the failover conditions and the traffic splitting, you just show the system a million logs of past network requests and basically tell it, figure out the optimal routing rules yourself.
I mean, that completely flips the traditional engineering paradigm. You're no longer writing the logic. You're providing the historical data and you're forcing the machine to write its own logic.
Exactly. And if you've spent your entire career mastering deterministic systems, that transition can feel honestly deeply unsettling.
Oh, absolutely.
Because, you build an architecture on the Google Cloud platform, you expect it to do exactly what you programmed it to do. If A happens, do B. But you, the listener tuning in right now, are stepping out of that comfort zone.
Yeah, you really are.
You've already conquered the Google Professional Cloud Architect exam.
Mhm.
You have the network engineer and security engineer certifications. Like, GCP infrastructure like the back of your hand.
But the Google Professional Machine Learning Engineer exam is just a completely different beast.
Yeah.
It requires this massive shift from deterministic thinking to probabilistic thinking. You're dealing with math that, let's be honest, you might not have touched since university.
Yeah.
And there's this entirely new vocabulary that masks concepts that are actually quite intuitive once you break them down.
And that is exactly our mission for this deep dive today. We want to translate the black box of machine learning into the systems architecture mental models you already possess.
Right. And to do that, we're going to dive deep into linear regression. It is the absolute bedrock of machine learning.
It really is. Like, before you can design complex neural networks or generative models, you need to understand mechanically how a machine learns to predict a simple outcome.
Because beneath all the hype, machine learning is just applied mathematics. It's a statistical technique used to find the relationship between variables.
Mhm.
Specifically, we're going to look at how linear regression predicts an output, which we call a label, based on its inputs, which we call features.
Let's lock those two terms in immediately because, well, the entire discipline hinges on them: feature and label.
Yep, super important.
So if I map this to my networking background, say I'm looking at my traffic logs, the number of active users currently hammering my application, that input data is my feature,
Sure.
right?
Exactly.
And the server latency I'm experiencing as a result, the outcome I want to predict is my label.
That is a very solid baseline analogy. If you plotted those two things on a graph with, active users on the bottom x-axis and latency on the vertical y-axis, you'd see a trend.
Right, they go up together.
Yeah, as the number of users goes up, the latency generally goes up.
Mhm.
Linear regression is basically just the mathematical process of drawing the optimal straight line through the center of that cluster of data points.
So you can predict future latency based on user counts.
You got it.
Let's use a classic physical example from our sources to visualize this before we hit the actual math. Imagine we want to predict a car's fuel efficiency, its miles per gallon.
Okay, so the miles per gallon is our label. It's the target outcome.
Right. And we are going to base that prediction purely on how heavy the car is, measured in thousands of pounds. That weight is our feature.
And intuitively, you know the relationship there. I mean, as a car gets heavier, its fuel efficiency decreases.
The line goes down.
Exactly. The line goes down, but the machine doesn't have intuition. It only has the equation.
And here is where we need to decode the vocabulary, because the equation itself is actually just basic algebra. It's y prime equals b plus w1 times x1.
Right. So let's strip away the Greek letters and just focus on the mechanics here. Y prime is simply your prediction.
So the miles per gallon we're trying to guess.
Yes. And X1 is your feature value. That's the raw data you feed the system. So if you have a 4,000-pound car, your feature value is just the number 4.
Which leaves us with the two variables that actually define the model, right?
Mhm.
B and W1, the bias and the weight.
Yep.
Now, I have to push back on this terminology a bit because if you're coming from a standard IT background, those words carry completely different baggage.
Oh, for sure.
Like, bias usually implies a flaw, like a cognitive prejudice or a loaded die, and weight just means heaviness. For an IT engineer stepping into ML, how should they visualize this so they don't get confused?
It is a massive point of friction. I agree. You really have to scrub those everyday definitions from your mind. In machine learning, bias is just your mathematical starting point. It's the way you intercept.
Okay, so the baseline.
Think of it this way. If you knew absolutely nothing about a car, like if its weight feature was mathematically 0, what is the baseline miles per gallon the system would assume? That anchor point is your bias.
Oh, I see. So it's the default baseline before any conditions are applied. Okay, and what about weight?
Weight is the important style. It represents the slope of your line. It basically tells the equation, for every single unit of input I receive from this feature, how aggressively should I change my final prediction?
Let's plug in some actual numbers from the source to see that engine turn. Imagine we drew that line of best fit through our car data. The math tells us that the bias, our baseline starting point, is 34. And the weight, the important style for the car's heaviness, is negative 4.6.
So your equation is predicted miles per gallon equals 34 plus negative 4.6 times the future value.
Right, so if I input a 4,000-pound car, my feature value is 4. I multiply 4 by my weight of negative 4.6, which gives me negative 18.4.
Following you so far.
Then I add my baseline bias of 34, and I get 15.6 miles per gallon.
And that's the deterministic part of the process. Once a model is finalized, it's really just a calculator. You put a number in, you get a number out.
Right.
But the critical architectural question is, how did the system figure out that the bias should be exactly 34 and the weight should be exactly negative 4.6?
Yeah, because we didn't program those numbers. The system found them. And that brings us to the actual learning part of machine learning, the training phase.
Exactly. During training, the model's entire objective is to optimize those two parameters, the bias and the weights.
How does it start? Just at 0.
It usually starts with random guesses for both. It seeds the historical data through its random equation, looks at the prediction, compares it to the actual historical outcome, and basically realizes its guess is terrible.
And here is a crucial rule for the exam, right? Listeners, write this down. During this entire training loop, what actually changes? The raw data, the features, and labels never change.
Never.
The only things the algorithm is allowed to tweak are the weights and the bias.
Exactly. But to tweak them effectively, the algorithm needs a feedback loop. It needs a way to quantify exactly how terrible its guess was. And this is what we call the loss function.
Okay, so is the loss function similar to an error rate in networking? Like, monitoring the percentage of dropped packets to trigger an alert?
It's a little more nuanced than a simple percentage, but yeah, similar concept. The loss function measures mathematical distance.
Yeah.
So if the model predicted 15 miles per gallon, but the historical data says the car actually gets 25 miles per gallon, the loss function calculates the magnitude of that error.
Ah, I get it.
It aggregates the errors across thousands of data points to give the model a single score of how bad it's currently performing. And the goal is to drive that loss score as close to 0 as possible.
Okay, so the model has a score telling it that it's failing, but how does it know how to fix it? Like if my weight is currently set at -2, how does the machine know whether to adjust it to -3 or -1? It can't just guess randomly forever, right? That would burn through way too much compute.
Oh, way too much. And this is where we introduce gradient descent. This is really the navigational engine of machine learning.
I've always struggled to visualize gradient descent. It just sounds like advanced calculus.
Well, the underlying math does use calculus, specifically derivatives, but you don't need to write the proofs to understand the mechanics.
Thank goodness for that.
Right. So imagine you were standing somewhere on the side of a steep, rugged mountain, and it is pitch black. You cannot see your hand in front of your face.
Okay, I'm blind on a mountain.
Yes. Your only goal is to find the lowest point in the valley. How do you do it?
Well, I can't see the valley, so I guess I'd just, feel the ground under my boots. If the ground tilts downward to my left, I take a step left. If it tilts downward to my right, I take a step right.
Exactly. You calculate the slope of the ground immediately beneath you, and you step in the direction of the deepest downward slope. That is gradient descent.
Oh, wow.
The mountain is your loss function. The model calculates the mathematical slope of its current error, and it nudges the weight and bias dials in the direction that makes the error go down.
So it takes a step, recalculates the slope, takes another step,
and repeats until the ground levels out. When the slope is 0, you've reached the bottom of the valley. You've found the optimal weights.
That makes perfect sense. But let me push that analogy a bit further. If I'm on that mountain, the size of the steps I take matters immensely. Like if I take tiny, shuffling baby steps, it's going to take me 1,000 years to reach the valley.
Right. You'd exhaust your compute resources before the model ever finishes training.
But if I strap on a jetpack and take a massive 1,000-foot leap, I might completely overshoot the bottom of the valley and land halfway up the opposite mountain.
And then you calculate the slope, jump back the other way, and overshoot it again. You just bounce back and forth across the valley forever.
Thrashing.
Yeah, in systems architecture, you'd recognize that as thrashing. The model never converges.
So how do we control the step size?
That is handled by what we call hyperparameters, specifically one called the learning rate.
Wait, how is a hyperparameter different from a regular parameter, like weight or bias?
Great question. Regular parameters, weights, and biases are the internal dials the machine adjusts by itself during training. Hyperparameters are the external guardrails that you, the machine learning engineer, set before the training even begins.
Ah, okay.
You define the learning rate. You tell the model, take exactly the size of a mathematical step each time you run gradient descent. Tuning that hyperparameter correctly is the difference between a model that trains in 10 minutes and a model that thrashes indefinitely.
So is training kind of like an autoscaler in GCP? Like you don't tell the autoscaler exactly how many servers to spin up at 2 p.m., but you configure the behavioral rules it uses to make that decision without oscillating wildly.
That's the exact mindset. You are architecting the environment for the algorithm to succeed.
Okay, so we've mapped the mechanics. We know how a model uses gradient descent to adjust a single weight and a single bias to predict miles per gallon based on car weight. But let's be real, predicting fuel efficiency just by looking at the heaviness of a vehicle is overly simplistic.
Yeah, way too simple.
A massive pickup truck and a low-slung aerodynamic sports car might weigh the exact same, but their fuel economy will be drastically different because of aerodynamics, engine size, and gearing.
Which means our single feature model is going to have a very high limit on how accurate it can ever be. To solve complex real-world problems, we have to scale the architecture. We move from simple linear regression to multiple linear regression.
We give the model a whole dashboard of inputs. We don't just feed it weight. We feed it engine displacement in cubic centimeters. We feed it acceleration speed. We feed it the number of cylinders and the total horsepower.
And mathematically, the equation simply expands to accommodate this. Instead of one weight dial, you have a massive mixing board.
Right.
The equation becomes I prime equals the baseline bias plus weight 1 times feature 1 plus weight 2 times feature 2 plus weight 3 times feature 3, and so on. Every single feature gets its own dedicated importance dial.
But this raises a major architectural question for me. If I'm feeding the model 5 different features, does it calculate all 5 weights simultaneously during gradient descent?
It does.
Because in my head, I'm imagining a scenario where features overlap. Like, what if I feed it the total horsepower and I also feed it the number of engine cylinders? Aren't those two inputs basically measuring the same underlying physical truth?
Mostly, yeah.
A car with 8 cylinders naturally has more horsepower than a car with 4. Does the model get confused by that redundancy? Does it automatically figure out if horsepower is more important than the number of cylinders?
You've just identified a massive challenge in ML called collinearity. When two features are highly correlated, like horsepower and cylinders, they essentially compete to explain the same variance in the label.
So how does the model handle the competition? Does it, like, blow up?
It doesn't blow up, no, but it has to balance the scales. During gradient descent, the model is looking at the entire mathematical landscape at once. It's not just walking down a 3D mountain anymore, it's navigating a multidimensional plane.
That sounds intense.
It is. But if it realizes that horsepower provides 99% of the predictive value, and the number of cylinders only adds a tiny fraction of new information, the algorithm will naturally shrink the weight of the cylinders feature closer to 0.
Oh, wow. So it effectively tunes out the noise automatically.
Exactly. It automatically learns the relative importance of every single feature in your dataset. It mathematically proves which factors actually drive the outcome.
That is wild.
Like if it turns out that acceleration time has an inverse relationship with fuel economy, which it does, slower cars are generally more fuel efficient, the model will assign it a positive weight to offset the negative weight of the car's heaviness.
That is incredibly powerful because, as a cloud architect, if you ask me to manually write the conditional logic for how 5 dynamically changing variables interact to predict a single outcome, the script would be a brittle nightmare of nested if-then statements.
Oh, it'd be awful. And the moment a new variable was introduced, the entire script would break. That is exactly why ML is eating software. You don't hard code the conditional logic, you just build the data pipelines to feed the features into the model, and you let gradient descent figure out the exact mathematical relationship.
Let's bring all these threads together and summarize the core lessons you need to carry into the exam, because we've covered a lot.
We really have. But it all boils down to this machine learning is just applied math finding patterns.
Right. Your features are your inputs, the raw data. Your labels are your outputs, the target you want to predict.
The model itself is just an equation. It consists of a baseline bias and a series of weights that act as importance dials for each feature.
And training is the automated process of optimizing those dials. The model makes a guess, measures its error using a loss function, and uses gradient descent to step blindly down the mountain, tweaking the weights and bias until it finds the lowest possible error.
And you control how fast it walks down that mountain by setting hyperparameters, like the learning rate. And crucially, during this entire process, the original data never changes, only the parameters update.
The leap from cloud architect to machine learning engineer isn't about learning magic. It's just a different type of system architecture. You already know how to route data, how to scale compute resources, and how to monitor system feedback loops. Now you are just applying those same structural principles to the internal math of a statistical model.
Beautifully said.
Which brings us to a final, slightly provocative thought to chew on as you study this module. We spent this whole time talking about how the ultimate goal of training is to drive the loss function down to 0. We want the model to perfectly minimize the difference between its predictions and the actual historical data.
Right, the bottom of the valley.
Exactly. But think about this from a security engineering perspective. What happens if you build a firewall that perfectly memorizes the exact IP addresses of every past attack to the point where its historical error rate is literally 0, but it has no idea what the underlying behavioral pattern of an attack actually looks like?
Well, the moment a threat actor changes a single digit in their IP address, the firewall fails completely.
Exactly. So in machine learning, if your model adjusts its weights and biases so intricately that it perfectly hits every single historical data point without a single error, is it actually learning the general trend? Or is it just blindly memorizing the past?
That phenomenon is called overfitting, and it is the ultimate enemy of a machine learning engineer.
A model that perfectly memorizes the training data is useless in the real world because the real world is full of data it has never seen before. Balancing the tension between accurately learning the past and remaining flexible enough to predict the future is the true art of ML engineering. It's something you will spend your entire career managing.
It really is the hardest part of the job.
So we'll leave you to ponder that tension. Keep building, keep studying those system mechanics, and good luck on the exam.